Hey everyone, welcome back to Calculus 2. This is lecture 10 of the course, and in this lecture we're going to start discussing volume, and specifically using the definite integral to identify the volume of a surface, or sorry, of a solid created in three-dimensional space. Now, when we get into Calculus 3, we'll talk about other ways to calculate volume. We're going to start out with sort of a more simplistic and more basic idea of calculating volume. And that method that we're going to start with is called the disk method. Okay, so let's jump into this. This will be section 2.2, the disk method. Okay. So, the kinds of solids that we're going to begin our work with on volume with are going to be of a particular type. They're going to be called solids of revolution. Okay, i.e. revolution meaning revolving. Right, we're going to have solids that are built by revolving. And so let me start by giving a kind of a description in words, and then we'll draw some pictures. So if a region in the plane is revolved about a line, okay, the resulting solid is called a solid of revolution, and then the line is called the line of revolution. Or sorry, maybe the axis of revolution. Okay, so this is kind of a in words sort of description here. Let's draw some pictures quick. So let's say I've got a line here, and off of it I build a rectangle. All right, now if I were to take this rectangle, it's a planar shape, right? And I rotate it around this line, what I might expect to get is something that looks like this, right? I would get a cylinder, right? So you can imagine this would just kind of rotate around. This would rotate around. You'd end up with a cylindrical shape, right, like this. Similarly, if I start with something like a semicircle in the plane, and I rotate a semicircle about an axis in the plane, then what I might expect to get would be a sphere. Right, so here you get a cylinder, here you'd get a ball or a sphere. And you could do other things as well, like you could have something like, if I start with a triangle, and I revolve a triangle like this, then what am I going to get? I'll end up with a cone, won't I? Okay, all right, so that's a cone. And then, of course, these are just like the basic shapes, but you could do something really complex. If you wanted to, maybe I start something more complex. I go like this, and then like that, and then like that. Right? This is not exactly, it's not a rectangle or a triangle or semicircle, it's something kind of in between. But if I rotate that around this axis, then what I would expect to see is, something that looks a bit like a bottle or something. It's not exactly like this, but you get the idea, right? Right, if I were to rotate that. Right, so there's obviously an infinite variety of shapes that can be generated, kind of spun up in this way. and this is just just a smattering. But I think when you see these, it kind of helps to solidify in your mind exactly what a solid of revolution is. It's something that could be built from a plane, from a shape in the plane if it's rotated around a particular line, right? So you get things like cylinders, balls, cones, bottles, etc. Okay. Now the simplest example here, I would say, maybe not the simplest, but a simple example. We'll say it's the simplest. The simplest example might be a disc, which is a lot like a cylinder. Okay, so so if I were to start with, here's my axis of revolution, and I'm going to be rotating whatever I build on this thing in this manner. And if I just build a basic rectangle here, all right, and we'll just say this rectangle has a certain width and a certain height, and we'll just denote height by R, width with W. Why we use R here will be clear in a moment. Right, but if we do something like this, then you could see that, this is kind of similar to what we did with the cylinder, right? And what's going to be spun up is going to be a disc. Right, so it'll have a certain width, just like so. Now the width of this thing is going to be the width of the rectangle, right? Remember, this is going to spin around and make this shape. There's going to be a center in here, and that is going to denote the height of the rectangle, but it's also going to, in the case of the disc, be the radius of the disc. So W is the width, and R is the radius. The radius, of course, comes from the height of the rectangle off the axis of rotation. Right, so here's our axis of rotation, right? It's spun like this, and this is the shape that we get. Okay? All right. Now let's talk about this disc. This is what we mean by a disc. It's kind of something that you imagine maybe has sort of a really narrow width, but some reasonable R. So it's a relatively kind of, you could think of it as a really short cylinder. Okay. So let's break this this disc down. I'm going to draw it on its side. So let's say it looks like this, right? And again, you're going to have this middle piece here, and that's going to correspond to some radius, which we'll call R, and then the thickness of the disc, which we'll call W. Okay. Now, a disc like this, right? Something like this, a shape like this, we can easily calculate a volume for it, can't we? So we can easily calculate a volume for this shape. Okay, now remember, when we calculate volumes, right, basically what we want to do is we want to calculate the base, the area of the base, and then multiply it times whatever the height, or in this case the width, happens to be. And so the base of this figure is a circle, right? So the area of the base is equal to pi times the radius squared. Right, just a simple circle. Right, so then that means then that the volume would be equal to pi times the radius squared, the area of the base, times the height, which in this case is W. Okay. Right, so important to remember here that R is the radius of the disc, and W is the height of the disc, or width, however you want to think about it. And to some extent, like height, width, it's irrelevant, like which one you choose, just so long as you know what you're talking about. Okay, it's the dimension perpendicular to the circle, okay, that's formed by the base. Okay, so now let's kind of take this and keep this in the back of your mind, sort of file this away for a moment, come back to it. But I want to shift to just an arbitrary region, and we're gonna see how these ideas connect. So consider a region. Okay, and so this region will be, we're just going to kind of keep it simple. It's going to look like this. And this is going to be some function here of, we'll say it's of x in this case. And we're just going to call it, I'm just going to name it r of x. Okay, and we'll see, obviously, I think, people see that r and they're like, okay, radius, that's going to have something to do with it. Just don't worry about that yet. We'll get to that in a second. Okay, and there's some region here that we're interested in. A to B, right? And so normally if we were to integrate here, what we would end up with is the area of this region between A and B, underneath of R, and above the x-axis, right? So we would get an area here. And so this area that we would calculate here is kind of like the area of the base that we saw in this previous example. Just kind of link those two in your mind loosely right now. Okay, but what we're going to do, well, first let's break this area down just a little bit more, and then we'll see what happens when we start to mess with it more. Right, so just redrawing the same picture, trying to make it look similar. Okay, so I've got my region between A and B. Okay, now inside of this, as part of the task of calculating the area here, we're going to have we would basically break this interval down into a partition of n subintervals, and on each of those n subintervals we would construct a representative some kind of a rectangle. And so what we're going to do is just kind of draw in a representative rectangle. Okay, when I say representative, I mean it's representative in the sense that it's just giving us some idea of sort of how this area works. Right, so of course the width of this would be delta x. Right, now this is a grotesquely large representative rectangle. It's just being drawn large just for the sake of making it clear what we're looking at. But the width of this is delta x. Then the height of the rectangle is determined by the function r, right? Right, so we would say the height here is r of x. I guess I should put that in there. Let's write r of x. Okay. Now what happens if I take this, and remember this is the x-axis here, y-axis here, what happens to this region and to this representative rectangle if I were to rotate the entire construction around the x-axis in this way, right? So rotate it around the x-axis. So what's going to end up happening to the rectangle is it's going to spin out a disk, right? We just saw that. That's what our previous example was. When we rotate rectangles around an axis of revolution, we get a disk, right? And so this representative rectangle becomes a representative disk when we rotate it. Okay, so that's what's going to end up happening there, right? So let me try to draw a picture. Unfortunately, some of this lecture is going to depend upon my artistic ability, so I'm going to do my best here, but hopefully you can visualize these things without the most perfect picture. Okay, so so here's kind of like the disk, right? So you've got the front of the disk here, and then the back side of the disk is behind it, right? And then right in the middle, you're going to have, this is your axis of rotation, right? You can see our disk is kind of in the middle, and so what's going to happen is this is going to come down, right? And you're going to have kind of the low part here, and then over here, it's just going to kind of continue on at the same height roughly, right? But this is like more or less what you might expect to see if I were to rotate this region about the x-axis, right? And here's Our disk starts out like this, and it sweeps out, or sorry, our rectangle starts out like this, and it sweeps out a disk. Okay, so that's the idea. Now, when the rectangle is rotated and it goes from being a representative rectangle to a representative disk, it's going to basically go from having just an area to having a volume. And so that volume can be calculated, right? So the volume of the representative disk is going to be what? I'm going to call it delta V. Okay, that representative volume. And it's going to be basically you can think of it as the surface area of the circle that's swept out, right, which is going to have height r, right? So it's going to have pi r squared in it. That's going to be the area of one piece of this, and then times w, right? Well, in this case, it's delta x, right? So it's going to look like this. So the representative disk will have a volume of pi r squared times delta x. Okay? All right, and so this is the construction. This is the idea behind the disk method. So you start with a representative disk like this, and then what you're going to end up doing is making this partition increasingly small, right? And the entire shape will, at the end, eventually consist of just an extremely large number of representative disks. So each one of these is a representative disk. Okay, and each one of them is going to have a volume that can be calculated using this exact formulation. And when you add all of those up, all of those little volumes of the representative disks, what you're going to get is the volume of the shape overall. Okay, so let's look at what that calculation looks like. Okay. So approximating the volume of the solid by n disks of width delta x, okay, and radius r of x. Each one of them could potentially have a different radius, right, based on the function r. So approximating the volume of the solid by n disks of width delta x and radius rx produces the following. Of course, you're going to have the volume approximately equal to the sum I equals 1 to n, right? We're going to add up the volume of all those little disks. Now each of those little disks is going to have a pi in it. It's going to have the radius squared, but because the radius is going to be different, we have to use the function r. And they're each going to get multiplied by their width, which is all the same, in this case delta x, right, like so. So this is what it looks like. So each, for I equals 1 up to n, you're going to have pi r squared times delta x, right? And here the r will vary because of, depending on which part of the shape you're in. Okay, and then this can, of course, be cleaned up slightly. You can pull the pi out front in particular. Okay, we'll write it like that. Now, this approximation, of course, this is an approximation. Note, approximation. This approximation will become increasingly accurate, right, as the norm of the partition decreases, right? So as the number of representative disks increase, the accuracy of the volume calculation will increase as well, right? So then basically what we can say is that as the norm of the partition goes to 0, which, i.e. n goes to infinity, the number of disks in the approximation increases to infinity. So as that happens, the volume goes from being approximately this thing to being precisely this thing. So we'd say the volume is equal to the limit as the norm goes to 0 of pi times I equals 1 to n r of x xi squared times delta x. And we would say that, of course, this is just a Riemann sum with a square term in here, and so this would just be equal to the integral from A to B of r of x squared dx. Okay. Okay, so basically, to find the volume, you just need to know this r function, and you square that, integrate, and then multiply everything by pi, and that gives you the volume. So, just to notice that this is all based on, the basically pre-calc formula. The volume equals pi r squared w. All right, so it's all just based on that simple area of volume of a cylinder or disk, and it's just been expanded to produce a formula for the volume of not just the disk now, but a general solid of revolution. So this has been expanded to a formula about all solids of revolution. Okay, so V equals pi times the integral from A to B of Rx squared dx. All right, perfect. Okay, and so this is the disk method. Right? This is the disk method right here. Now, as we've been kind of building it up, we've been kind of assuming, in our kind of workup here, that the axis of rotation is the x-axis. I think in our motivating examples at the beginning, our axis of rotation was was the vertical axis. When we were drawing bottles and cylinders and cones and things, right? So it can work with either orientation. So if the axis is horizontal, then the volume is equal to pi times the integral from A to B of what we just basically the same thing as this. If the axis is vertical, right, if it's a vertical axis, then that means the formula will change, and instead of integrating with respect to x, we'd be integrating across the y-axis. And so we'll write c to d of r of y squared dy. Okay, so we'll talk about this in a second, but this is basically the two kinds of the two basic flavors of the disk method, right? And actually, this is a particular case of the disk method, which we'll talk about in a moment as well. We'll generalize this ever so slightly, but we're going to start with this and use this to do a few examples. Okay, so just to underscore this, let's talk about what do I mean by horizontal and vertical. Well, I mean, I think you probably have a sense for what I mean, but let's just make sure. So if it's horizontal, that's what we've been describing, right? That's where you've got, some function. You've got your A to B, your representative rectangles have width delta x, right? Some width on the x-axis. This is the x-axis, right? We're rotating around here, right? And then you've got r is a function of x here as the height, right? This is what we mean by horizontal. And so in this case, the volume is equal to pi times the integral from A to B of r of x squared. That's what that one looks like. Now, what do we mean by vertical? Well, vertical just means that similar setup, right? It's just that in this case, the axis that we're spinning around is the y-axis. So this is the x-axis. And so what's important there is then, maybe I have C and D, is that my representative rectangles are always going to be perpendicular to the axis of revolution, right? And so this would now be a delta y. It'd be a width on the y-axis. And this would be an r of y, a function of y, rather than a function of x. Right? And so that's why we have a different formula for the vertical axis of revolution. And it's similar. I mean, it's pretty much the same. It's just you're reorienting given the change in the axis. Right? So here it's a function of y, and you're integrating, of course, across the y axis. So remember when we integrate, the dy it basically tells you where the base of the representative rectangles are. So if it's delta y, then that means it's on the y-axis. If it's delta x, that means it's on the x-axis. Right? And so when we add them up along the delta y's or along the delta x's. Okay, so that's why you see delta x dx, and that's why you see delta y dy. Okay. All right. Good. Let's talk through an example or two here. So the simplest examples will probably involve a region bounded by the graph of f and the x-axis. All right, so let's do an example like that first. So find the volume of the solid formed by revolving the region bounded by, here's our function, f of x equals the square root of sine of x, and the x-axis on a particular interval 0, less than or equal to x, less than or equal to pi. Right, now we're revolving about the x-axis. Okay, so these problems are a little wordy. Find the volume of the solid formed by revolving the region bounded by square root of sine x, the x-axis, about the x-axis. Right, so what I like to do is just kind of start by drawing it, or pull out a graphing utility and visualize the thing. Right, so this is the square root of sine of x, right, and so it's going to go, and we're interested in between 0 and pi. So it's going to look a bit like this, not exactly like this, but something like this. Okay, this will be pi, this would be 0, kind of comes up, and this will be 1, reaches a max of 1. And so your representative, and remember this is the x-axis, right? So it's being rotated like this, right? And so if that's the case, and we're using the disk method, then our representative rectangles will be based off of the axis of revolution, it'll be perpendicular to that. So we'll have a delta x, and the height here is going to be r of x. Right, and of course r of x is just going to be the square root of sine of x. Okay, so we got all the pieces there, right? So we can set up this integral and calculate it. So the volume would be equal to, let's write the formula out, pi times the integral from a to b of r of x squared dx. So just plug in all of our things here. So we got pi, and now the integral will go from a to b, which is in this case 0 up to pi. Okay, and then r is just the square root of sine x, and we're going to square that and integrate with respect to x. Okay, so this one is nice and easy to do, right? The square of the square root means we're just integrating the sine function. And so what do we get when we integrate the sine function? Well, we get negative cosine of x. Okay, and we're going to integrate from 0 up to pi. So we get pi on the outside, and then negative cosine of pi would be negative negative 1. So we'll put negative negative 1 there, and cosine of 0 would be 1. Right, and so when you do all of this, you should see, oh, it should be like that, because it's negative cosine, right? So you should get 2 pi. Okay. All right, very good. So this is the volume of this figure, when it's rotated like this. Now, what does this figure look like? Well, it's kind of like a football, maybe. You know, it's going to have. Oh, that's not very good. Let's do it this way. It's going to look a bit like this, or a flying saucer or something, maybe. Right, here's your axis of rotation, obviously. Right, and it's going to have some. Maybe it's like a lemon or something. It's going to have some kind of a curvature there. That's a terrible picture, but all right, so that's our first example. Very good. Now let's take another example, and these examples will get increasingly difficult, right? That one was very straightforward. So let's take a look at another one here. Find the volume of the solid formed by revolving the region bounded by f of x equals 2 minus x squared and g of x equals 1 about the line y equals 1. Okay, so here notice that so find the volume of the solid form by revolving the region bounded by f and g, these two functions, and revolving it about the line y equals 1. So notice we're not revolving around a coordinate axis here. Okay, so here we are not rotating about a coordinate axis. So this is going to change the way this has to be thought about a little bit. Okay, so let's draw this thing out to start with. Okay, so we're going to put our xy axis, and again, just pop open Wolfram Alpha, drop these two functions in, ask it to plot them, and that's, you know, the best way to go. So here I've got maybe 1 and 2, and so this f function is basically an upside down, it's a quadratic function that is shifted up 2 spots, right? So it's going to kind of look like this. Okay. Sorry, this is x-axis, this is the y-axis, this is 1 and 2. And then, of course, g is just a constant function that comes across like this, right? So this is f of x, and this guy here is g of x. Right, and so the region that's bounded by these two is just this little piece here. Okay. And so that's the region that's bounded by f and g, and it's this region is going to get rotated, but it's not going to be rotated around the x-axis, it's going to be rotated around the function g. So it's being rotated about the line y equals 1, which is g itself. Right, so it's going to rotate around this. Okay. So a couple of things here. Like this one is more complex, has more nuance to it, and is not as quite as obvious as the previous example. So let's talk through each of the pieces here. So the first thing that we might want to do is figure out what are these bounds. So that we're not explicitly told what the bounds of the integral are going to need to be, but we can find them by equating f and g and solving for x, right? So f of x equals g of x, right? We'll start with that. So 2 minus x squared equals 1. Okay, and then that's going to mean that negative x squared equals negative 1, which means x squared equals 1, which of course means x is equal to plus or minus the square root of 1, which is just plus or minus 1, right? So this must be 1, 1, right? So, this is 1, 1, that point up there, and this would be negative 1, 1. Okay, so this must be negative 1 on the x-axis, and this would be positive 1 on the y-axis. Okay, perfect. So that means our a and b is going to, our integral is going to go from negative 1 up to positive 1. Okay, now what about the radius here? I'm going to draw another picture. So this is the part that So this is our region up top here, and our representative rectangle is going to be here, and so this would be the the y-axis, and then the x-axis goes like this. Okay, so of course you've still got your delta x in here, right? So we've still got the delta x. And so what about the radius though? Well, r of x, if the function f is our r, so if r of x is equal to 2 minus x squared, right, that's going to tell us the height all the way up to this line, right? But we actually don't want the height to be that, right? We can see that our representative rectangle starts at G and goes up to R, right? So our radius is actually going to be different here, right? Because our axis of rotation is not a coordinate axis. So our r of x is not that. Instead, our r of x is going to be the function f. That's this thing here. So it's the distance from the x-axis all the way up to this function. But we don't want to include this part, right? This part needs to be excluded. So it'll be f of x minus g of x. Okay, right? So hopefully that's clear. So this r of x is all about the height of the representative rectangles, and it's going to start at the x-axis and go all the way up to here, but then we want to remove the part that's below g, right? And so that just means f of x minus g of x, which for this example is going to be 2 minus x squared, that's the f of x, and then minus g of x would be minus 1. G of x is a constant. Okay, so r of x here is going to be just basically 1 minus x squared. Okay? All right, so that's a little tricky. It can be a little bit tricky. Just keep in mind that r, whatever the function is for r, it has to be a function of x in this case, because the axis of rotation is the x-axis. Well, it's horizontal, not necessarily the x-axis. But it really has to be the height of the representative rectangles. Okay, that's what r of x really is. All right, so we have all that we need. We can set up our integral. So the volume here is going to be equal to pi times the integral from -1 to +1. Again, we found those values here by setting f equal to g, finding the intersections there. And then it's just going to be r of x squared. So r of x we just calculated as 1 minus x squared. Okay, and then we integrate. All right, and so this is pi times the integral from -1 to 1, and then you can just expand this if you want. You could probably use like a u substitution as well, but maybe it's easier just to expand it. So it's 1 minus 2x squared plus x to the 4th. Okay, and so what do we get here? We get x minus 2x cubed over 3 plus x to the 5th over 5, and that's from -1 up to +1. Okay, and then we can plug in our values here. So we're going to evaluate everything at 1, then everything at -1. So I'll do it down here in this next line. So it'll be pi times, it'll be 1 minus 2/3 plus 1/5. And then after that, we'll subtract -1 plus 2/3 minus 1/5. Okay, so it looks like that. Now, just if you wanted to do this, with the fractions, you just have to get common denominators, right? And so this would be like 15 minus 10 plus 3 over 15, and then minus, and then it would be -15 plus 10 minus 3 over 15, right? And so you get pi times 8/15 minus -8/15, right? And so what do we get? 16 pi over 15. Okay, so you got the pi in there. So this is, you could plug this into a calculator and get like an approximate, like decimal approximation here. But that's the idea. right? And so this is a more complicated example, but you can see that it kind of follows all of the ideas that we initially laid out. Now, this one particular this idea of having the radius be some kind of a hybrid is a good sequitur into this slight modification of the disk method that makes it quite a bit more powerful. So the disk method can be extended to cover solids of revolution with holes. Okay, so holes. What do we mean by holes? Well, holes are well, I'll draw a picture in a second. Okay, so the disk method can be extended to cover solids of revolution with holes, and sometimes people call this the disk and washer method. Okay, so it's really just the disk method, but it's like with the radius being a particular kind of thing. So here's the setup for the disk and washer method. It's really just a generalization of the disk method. But basically, here's the setup. So say I've got my x-axis. I'm going to revolve around this thing. Okay, and I've got my rectangle over here. It's going to have width w. Right, but it's not going to come all the way down to the x-axis. It's going to be some distance off of the x-axis, the axis of revolution in this case. And so what we'll do is we'll call this the outer radius. So it's the distance from the axis to the top of my rectangle. And we'll call this little piece here the inner radius, and we'll denote it with a little r. So big R is the outer radius, and little r is the inner radius. Okay, and so then of course we know that this piece here would be equal to the distance from the x-axis all the way to the top minus the x-axis to the bottom. So this would be r minus r. Okay. Now what's going to happen if I were to spin this rectangle around the x-axis, if I were to start rotating this whole construction? Well, what you'd end up with is something that looks similar to this, not exactly like this necessarily. All right, so you'd have kind of the disk just like before, but then you'd also have kind of a cutout here in the middle, wouldn't you? Right, and so the axis of rotation will go right through the middle, right? And so this piece here, so from here all the way to the bottom, that's your big R, right? That's that. And this piece here, this little r, that's just this. Okay. And then of course this piece up here, that's big R minus little r. Okay, so you can kind of see how all of these things kind of fit together, right? But so this is an example of a solid of revolution with a hole. It's got, it's like a ring or something, or a link, or a washer. I guess that's like a washer, like from your hardware store. If you go into your hardware store and ask for a washer, you'll get something that kind of looks like this. Okay. All right. So what's the volume of a washer like this? Okay, what's the volume of this shape? Well, you can think of it as, so the way you can approach the volume here is you take the volume of the whole disk, right? So the volume of the disk, and then you could subtract off what the volume of the hole would be, minus the volume of the hole. Okay, that would be the volume of the washer. So the volume of the disk is just pi r squared, right, times w. Well, start with the area. So actually, I want to start with the area. All right, so the area would be found by taking pi times the radius squared. So pi being the circular piece of it, and then r, the big R being the outer radius. So pi r squared minus the inner piece would be pi times the little r squared, right? And then the whole thing has to be multiplied by, so this gets you the area, right, of the base. Right, so this would be the area of the base of the washer. And then if you multiply that whole thing by W, you would get the volume. Okay, so it would be pi, so volume would be equal to pi r squared minus pi little r squared times W. And so we could clean this up a little bit, and we would get pi times, going to pull the pi out of there, pi times W, and then it's just r squared minus little r squared. Okay, so that would be the volume of the washer. Okay, perfect. Right, and so then you can basically, all that's changed here is instead of just r squared, it's r squared minus little r squared, right? And so the volume of the washer, the volume in the disk and washer method looks real similar to what we saw last time, to what we saw with just the disk method. It's just going to be v equals pi times the integral from a to b. And now instead of just r squared, it's r of x squared minus little r of x squared, right? So this is squaring. I'm going to be careful here. All right, so we're squaring the whole function here. Okay? And so this is basically just find the volume based on the outer radius and subtract off of that the volume based on the inner radius. Kind of like what we saw here. Find the volume of the whole disk, find the volume of the hole, subtract the hole from the disk, you get the washer. Okay. So that's the idea. Okay. All right, so let's do a few examples making use of this. Okay, so this allows us to do very complicated shapes, actually. Let's start with this shape here. So find the volume. I'm going to write the problem out. Find the volume of the solid formed by revolving the region bounded by the graphs of, now here's the function y equals the square root of x and y equals x squared about the x-axis. Okay, all right, so find the volume of the solid formed by revolving the region bounded by the graphs of y equals square root of x and y equals x squared about the x-axis. Let's draw this. Let's draw a picture. Okay, so we've got our x-axis. We know we're going to rotate around the x-axis, so let's denote that as such. Now, this will be drawn a little bit larger than normal. Right, so this is 1, this is 1. Now, yeah, if you just plug these two functions in at Wolfram Alpha or something, you'll be able to see that it's going to look a bit like this. Okay, this top one, the top function is y equals the square root of x. The bottom function is y equals x squared, right? So you can imagine y equals x squared, just a parabola here, and then you can imagine the square root of x, you know what it does, right? So it kind of comes like this and heads up. Okay, so our representative rectangles are going to be inside of this figure. Okay, And yeah, so I'm just going to take that representative rectangle and kind of blow it up over here. Okay, so the width of that is going to be delta x. Okay, now notice the rectangle is off of the axis of rotation. Right, there's going to be some big R here, right? Some big R, and that's going to be the square root of x, right? So the height is, the outer radius is going to come from the x-axis all the way up to the upper function, which is the square root of x. So that's R, big R. Little r is going to be this piece here, which is going to be it's going to kind of guide where the lower edge of the rectangle is, and that's going to be the other function, y equals x squared. So little r is going to be equal to x squared. Okay, so that's the setup. That's the setup, right? And you can imagine what this is going to look like, right? If this thing gets spun out, it's going to look, you know, kind of a bit like this. Try not to do too bad of a job here. It's going to be kind of like a bowl, isn't it, on its side? Right? I mean, it's going to have some thickness to it, right? So it's going to kind of, it's going to look like this on the outside. Oh, sorry. It's going to look like this on the outside, but then on the inside, it's going to be kind of like a more conic shape. It's going to have kind of a convexity to it, or concavity to it, I guess. So it's going to look a bit like this. All right. And so our task is to find the volume of this thing. Right? And so the volume is going to be equal to pi times the integral from a up to b. Obviously, we need to use the washer method because we got this gap between the lower portion of the representative rectangles and the axis of rotation. And so we're going to use an rx squared minus little r of x squared. And because the axis of rotation is the x-axis, we're going to be integrating with respect to x. So plugging all of that in. Oh, actually, we don't know what a and b are yet, do we? We don't know what these intersections are. Well, this one we can guess is 0. We would be correct there. But what about this other one? Now, what about the upper one? Well, we could set x squared equal to the square root of x, but you could also see that this is going to be 1 and 1, right? 1 squared is 1, and the square root of 1 is 1, right? So this is 1, 1. Okay. Now you could, as I said, you could set x equal to the square root of x, and you'd find out that the two intersections are 0 and 1. Okay. So our integral is going to go from 0 up to 1. Okay, along the x-axis here. And the outer function is the square root of x. So we've got the square root of x squared. And the inner function is x squared. We've got the inner function squared. And the whole thing is integrated with respect to x. And so what do we get? We get pi times the integral from 0 to 1 of x minus x to the 4th. It should look like that. Okay, and this is just a simple polynomial, so we can quickly integrate this. It'll be x squared over 2 minus x to the 5th over 5, and then from 0 up to 1. And so we can plug those values in. And what do we get? 1/2 minus a 5th. And then it's 0 and 0. And so this would be pi times, it'd be 5 minus 2 over 10. So what, 3 pi over 10? There we go. Okay. Perfect. Okay, so we're making a lot of progress here. All right, very good. Let's do another example. Actually, I think I'll pause the video here, or stop the video, and we'll have a part B with the rest of the examples. Okay?